Hi everyone. We'll be starting the class soon. Yeah. So last week we stopped with the assignments. I think for assignment number 4, right? And just give me a second. Hmm. We were looking into the measurement model approach. We were looking into how we can use the equivalent electric circuit in order to model the system. It is advantageous over what to say over the KKT method because you don't need the data over the entire range of frequency. So whatever is available, it tries to fit in and give you the values. And then we saw the choice of circuit where we saw Maxwell, Voigt, and ladder circuit. Then we saw how much confidence we should have, like how to take into confidence of fitted model, how many RC elements you need in order to fit the system, etc. Then we looked into zeros and poles. Sorry. Yeah. So then we looked into zeros and poles. We looked into zeros and poles, and then what is charge transfer resistance, what is polarization resistance, how physically, like once like impedance data is given, like how you can say like what circuit can fit, how many elements of RC combination do you need in order to fit it, and how can I visually say it is what was it? Mm, what was it? Like what is the RT value, what is the RP value, everything we had seen in the last class. So yeah, we looked into the void circuit when R and C are in parallel, and this corresponds to solution resistance. Then we saw like if there are two loops, then there will be two RC elements, and then can either be fitted using two void elements, or can be Maxwell with two RC, or Maxwell or a ladder also with two RC. Yeah. Then we saw like how many elements do we need in order to fit them. What will happen if you actually need two and you add more? You'll see that the error associated with that will be very high. So that's how we can say. Then, yeah, we saw the Maxwell circuit, ladder circuit, and void circuit. When R and C are in parallel and many such are arranged in series, it forms a void circuit. In Maxwell, you have one capacitor resistor in parallel, and then every R C will be then in series. Then we saw ladder where ladder is then R, and then you have the next capacitor and the resistor in parallel. Again, from that resistor, you have the next parallel. So it goes on. So we also saw like if it is void circuit, you cannot completely say this corresponds to double layer capacitance, and the other factor can not be attributed completely to the Faraday reaction. On the other hand, such a differentiation becomes easier in Maxwell and ladder, where I say this corresponds to the double layer capacitance and the solution resistance, and whatever left over is ZF. Such a thing cannot be done in void. So that is a limitation when you're using void. Physically interpreting becomes difficult when you're using void. Yes, then we saw like how to guess the circuit from the impedance data. You have a single semicircle, you'll have one RC in parallel. Starts from zero, solution resistance is zero. Your solution resistance is zero. And then if it is not starting from zero, it means that extra amount is response to RS value. And we are having a resistor in series with the RC in parallel. When two loops are there, you can ask the center will be two RC. So either you can go for the void or a Maxwell or a ladder. Okay. The thing is, they can be all the three can be used. So it's like distinguishability in the sense. whatever circuit you use of the three, the total impedance is going to remain the same, but doesn't mean that the individual values of the capacitor or the resistor in each of them becomes equal. That we then saw how to do. So three loops are seen, three in RCs in parallel. We saw how it comes, and this R into C, the product is time constant. It's tau. So when tone and when the toe, individual toe of each of the semicircles are not distinguishable, are not very far from each other, very close to each other, then what happens is the semicircle kind of gets merged as in this case and it becomes difficult to understand. We have to fit it in once, I mean, visually it becomes difficult. How many elements one should use that we had understood there is an archaic information criteria where either we can find out the residue or the sum of the square of the error between the model and experimental value, or a more advanced, I mean, more reasonable one is AIC because it accounts for adding for the addition of each number of what to say elements. At the same time, it gives a penalty also for that particular addition. So that is what AIC was. And then a modified AIC is also there. Then distinguishability, where we say that this, and this, all the four are distinguishable. Like as told, the total impedance remains the same, but individually the values of the components changes. Then we saw RT and RP, resistance to charge transfer, resistance to polarization. Omega tends to zero. You at low frequency, whatever you get, that is Z equal to RP for resistance. And at high frequency, the resistance is equal to charge transfer resistance. So if you have a single semicircle, RT and RP are going to be equal. But when you have two semicircles or more, the one at the high frequency corresponds to RT and the one low frequency corresponds to RP. Here RT means this one and not from the origin. Okay, it's the diameter of the semicircle. Then we saw zeros and poles. How to find out? We just find total impedance. Equate the denominator to zero, you get the poles, and numerator to zero, you get zeros. And the problem here is you cannot have a physical meaning to assign to each of the values. So that's a difficulty. Then we saw the limitation, basically the interpretation, like inductor values negative and all, what interpretation you give, and then the initial guess values can be very, if they're poor, then if you're using software to fit the data, you will get very large errors. So fitting becomes difficult. Then we saw the assignment questions. So all this were related to, yeah, so this was a distinguishability where you know the values for R3, C3, R4, you needed to find R5, C6, and C6. You find out at omega tends to, so check this. First you find out omega tends to 0 and omega tends to infinity. You'll get two equations simultaneously solved. You'll get the resistor values. To find out the capacitor or the inductor value, you have to equate the total impedance. And let's just total impedance of one circuit equal to total impedance of the next circuit. So if you know the value of one capacitor inductor, you will know the other one also. The first step before that, you have to find out all the rest of values so that you have to equate omega tends to 0 and infinity, and that's how you do it. Right? So yes, this is where we had stopped last day. So now we'll be moving on to the next class. And for this class, let me first write down what the syllabus is for this class, and then we'll, yeah. So this is class 6. We'll be solving assignment number 5. So in this, we learned about single electron transfer reaction. Okay. Then we're seeing about the ferroferry system. Okay, so basically, till now, you see the how we started. We saw basics of electrochemistry, what working counter reference and all where, and then we moved on to what is impedance, what are the modes of getting the data. Then we saw the instrumental setup. like how what you should do, the strip noise ratio, what should be amplitude, and those things we saw. Then we moved on to KKT, so where it's flagging of the system and all. Then we moved on to the passive elements used for fitting the data. So basically, you use software like ZMN and all to fit it. Tester capacity reference they use. We learned distribution. So that's how the next week was. And now much more advanced version of impedance that we're going to see for next couple of weeks, and that is about the reaction mechanism analysis. So, how to predict the mechanism of a reaction from the given impedance data and all, we'll see in the coming classes. Okay, so we'll start with simple circuit models, and then we'll move on to an advanced one. So here we're mostly looking to first single electron transfer reaction and then the two-step reaction. Okay. So the first one is single electron transfer reaction. Then so this is the syllabus for this. I mean assignment number 5. Let's try to understand the reaction mechanism analysis. We'll be starting with a simple system, which is the ferropheric system. A ferropheric system because it gives kind of stable result, and if you're doing it properly, the system is more stable and you get the results properly. So it is easier to model the system. That's why we're going for ferropheric system. So this is the single electron transfer reaction that you're going to see. So the ferropheric redox coupled reaction is you have ferri becoming to ferro. It's a reversible reaction. Okay. So here, because the molecules are large, so we have to consider potassium ferrocyanide, potassium ferricyanide. So the cation, the potassium ions are very large. So sorry, the entire molecule, okay, the potassium ferrocyanide or ferricyanide, they are very large molecules, and water dipole cannot get strongly attracted to it because it's large in size. So we are considering just the ionic part. Okay, with that assumption, we're doing it. So if I say this is represented as A and this as B, I can say I'm just simplifying because if I'm going to write the step, it becomes easy. K forward and K reverse. This is how the reaction is going to be. Okay, let me write the next step. Wait, so that it becomes I can write it in continuation. A giving B plus E minus. You have forward reaction and reverse reaction. So what is the rate of the reaction? So like rate of the reaction is always the rate concentration, sorry, the rate constant into the concentration of the product raised to any, if any stoichiometry is raised to that or something, right? So here we have both forward and the backward reaction. So that's right, forward reaction rate minus backward reaction rate. So what is the forward reaction rate? It is KFA. If I write it, see one more thing I have to do. Instead of writing it like this, let me go back here. So let me see. Fe Cn6 4 minus. So what is charge of Fe here? Because you know what is this charge of cyanide? That is minus 1. So I can say X being the charge of iron minus 6 because it is Fe, Cn6. So sign it is minus 1. So minus 6, minus 1 into 6 equal to the total charge is minus 4. So this is Fe equal to 2. So this is charge is 2 plus. So here you understand that here the A, here ion is in charge 2 plus. So I can write Fe 2 plus. Why I'm writing like this? Because the redox couple here it is the ion whose charge is getting changed, right? So that's why I'm gonna write A is here Fe 2 plus. Now the next component is Fe Cn6 3 minus. What is the charge of Fe here? X minus 6 equal to minus 3 and X equal to 3. So here it is Fe 2 plus and here it is Fe 3 plus, which is undergoing redox couple. Fe becomes Fe 3 plus plus A minus. So I've written it like this because it is a charge of ion that is undergoing, uh, it's becoming redox couple. So here the forward reaction is Kf and the backward is Kr. So the rate of the reaction is the rate constant into the concentration of Fe2 plus minus Kr Fe3 plus. This becomes the rate of the reaction. Now, we learned in the first class that the rate constant in an electrochemical system is exponentially related to the potential. So, K becomes K0 exponential VEDC. This we saw in the last class. Let me substitute the same for Kf and Kr over here. Becomes Kf0 e to the power B EDC Fe2 plus minus Kr0 e to the power 90 BDC. So again, B is also, it depends on the position, depends upon forward or backward. So B Fe3 plus. Now what is the coefficient B here? B equal to alpha. Bf becomes alpha NF by RT. I have taken it because the backward and the forward, the charge transfer coefficient becomes different. So if I write it as B, it becomes D. It doesn't make sense, or it is no, it's deviating in nature. So I mean, deviating meaning I'm writing a wrong term, so I cannot write like that. Then BR becomes minus 1 minus alpha NF by RT. So after this, so as I said, alpha here is charge transfer coefficient. So now your first step is to write the rate of the reaction. So there is a particular like the way of to solve any of the problem, be it one step, two step, three step mechanism, or with any number of intermediate. This is how you have to solve. First step, write the rate of the reaction, and now the next step is to write the current. So next step becomes to write the charge transfer charge NF into rate of the reaction. So that becomes NF KF0 EBF EBC Fe2 plus minus Kr. There's a difference. Like this small k, this large k. Okay. So I should be careful while writing that. This small k actually. So KR e to the power BR E D C F E V plus. So this becomes a rate. So if I'm trying to model, experimentally do this, then what is the relationship between current and the potential? In the forward direction, it is kind of like this. In the negative, I mean, negative means in the opposite direction becomes something like this. So this can be modeled using this reaction, this equation number two. So that's how it is meaning. Now, but if you see here, the yeah, this much you have got. Now, how to do the impedance calculation? Impedance calculation involves linearization. Why linearization? Because the whatever potential you get at any point, it will be your DC potential, and along with you will be applying a small AC bias, right? So you have both DC component and the AC component. So I'm going to linearize it. How to do it? This becomes EDC plus EAC naught sine omega t. This is something you have to understand. Now the next one becomes, understand this. Now the next one is the, if I take the rate constant of the forward this thing, it becomes kf naught e to the power bf into e. When you're doing impedance, this I have written in terms of a DC current you are applying, you're getting this relation here you see. But when I'm coming to impedance, it has both AC and DC bias. So you have to write like this. So this becomes kf naught e to the power bf EDC plus EAC. Now kf naught e to the power bf EDC plus e to the power bf. What is EAC? Is not sin omega t. Okay. Now let me. Okay, so the next step is, okay. Sorry. I have made a mistake there. I should have noticed. I'm really sorry. This step is wrong. I made a mistake. So yeah, kf naught e to the power bf EDC EBF. I'm sorry. I'm really sorry for that. It was a mistake from my side. Now, you can. I all of a sudden thought it is down, not exponential. I just it is BF. Along with that, I thought it is down. It is down. So that's why I took the positive sign, not separated. You have to be careful. It is exponential to the of BF into EDC plus EAC. It's not exponential just BF into EDC plus EAC. So when you opening the bracket, it becomes E to the power BF into EDC into E to the power BF into EAC. Now, let me take this as such. Now, this one, that is the AAC part, this I can linearize. Because 1 plus BF. EAC is nothing but EAC naught sine omega t, right? Next term becomes BF EAC naught sine omega t square by 2 factorial, and it keeps on going. So the BF into EAC naught, it is small. So we can basically truncate it after second term. So I'm gonna from here I'm gonna just truncate it, and I'll get kf equal to kf naught e to the power bf EDC 1 plus bf EAC. This is the DC part, kf DC 1 plus bf EDC, right? So for a small overpotential, same way I can linearize it. Which one? The current. Linearization is applicable for a small current over potential. So, what are the formula of IF that we wrote? NF rate. Rate is KF naught. Rate is KF into this one is a rate. Fe2 plus minus KR Fe3 plus. Now I can write this linearized way, that is KF DC 1 plus B1 DF EAC Fe2 plus minus KRDC 1 plus BREAC Fe3 plus. Right? So this is the next equation. First important equation is how to write the rate of the reaction. So the rate of the reaction when uh, I'm writing in terms of EDC. But when I'm going to write it for the impedance, what happens is it should account also for the AC current. So this is how we count. Now the next step, this was in a steady state. Now how to find out the, what I can do is let me rearrange it. Okay. So I already know. I'm going to rearrange it. NF, just rearrange it and opening the bracket. KFDC Fe2 plus KFDC BF EAC Fe2 plus minus KRDC Fe3 plus minus KRDC BREAC Fe3 plus. This is the entire thing. Now see this. The first term is KFDC into Fe2 plus. We also have minus KRDC Fe3 plus. Okay. That is KFDC Fe2 plus minus KRDC Fe3 plus. Let's go back to the equation. KFDC into Fe2 plus minus KRDC into Fe3 plus, which is also a type of rate equation, right? Rate at what? It is in DC. This means steady state. So this one, so NF into this one corresponds to the steady state rate or steady state current. So which is IFDC. There is no what to say AC current applied to that steady state. So this term, when you have KFDC into Fe2 plus minus KFDC into Fe3 plus, the whole multiplied by NF, it becomes IFDC. So these two terms can be substituted by IFDC. So you are writing the equation to find out the total IF. IF equal to NF into, I'm going to separate it out, okay? NF, I'm going to group this, and this separately. KFDC, BF, this entire thing corresponds to IFDC. Plus, so the total current is supposed to be IFDC plus IFAC. So if I can say this one is IFAC. Okay. So IFAC equal to NFKFDC BF Fe2 plus minus KRDC BR Fe3 plus. Here n equal to 1 because the single electron transformation Fe2 plus becoming Fe3 plus. Okay, I forgot one term. Okay, you see the equation, it has EAC along with it. I forgot to write. So here EAC is in common. I can take EAC out, right? Now what is impedance? Impedance is EAC by IFAC. So this becomes NF BF KF DC Fe2 plus minus KR DC BR Fe3 plus. Yeah. So this is the impedance value. Now this is the impedance value. Yeah. This is the impedance value, and this impedance value is because of the Faraday reaction. Okay, but actually, so this is because of the Faraday reaction. But in actual case, you'll also have the double layer capacitance, right? So you know this is our solution. This is CDL double layer capacitance and the Faraday reaction. So this is what we have found out. Now double layer capacitance, and there's always in parallel. So the total impedance is going to be 1 by ZF plus 1 by double layer capacitance. What is 1 by CDF? That is j omega c. What? So ZF we already found out. CDL also we have found out. So if we are rearranging it and writing, becomes j omega CDL. So ZCDL is equal to 1 by j omega CDL. So because it's 1 by impedance of CDL, I'm writing it as j omega CDL. The DL means double leg plus 1 by ZF. It's already given us this value. Reciprocal of that. N value is 0, so I don't have to write it. F, BF, KF, DC, Fe2 plus minus BR, KR, DC, Fe3 plus. Right? So this becomes the impedance value. So we can plot it to understand how it will look like, right? So basically, if you're doing it for small perturbation, you wouldn't have mass transfer limitation. So in that case, when you are plotting it, this is for a 0 volt. Now when the O potential increases, becomes the circle dia becomes smaller and smaller. So when DC is changing, what is happening is the resistance changes. And you have the diameter is reducing in this case. So this is about the first simple electron transfer reaction. Now let's go to the two-step reaction. I hope this clear. So here we are considering a metals on which on the surface of, so basically when you have multi-ion metals and all, although we write it as a single step reaction in which one ion is getting transferred to another during dissolution and all, but it may actually involve multiple steps in order to achieve that. So that's the idea which we are using here. So let's consider a simple step, a simple reaction where you have a metal which undergoes dissolution. It forms metal adsorbed intermediate first. So metals undergoing dissolution forms N plus ions that should go into solution. It wouldn't directly go, we are telling. It first gets absorbed on the surface of the metal as in the form of ions. M forms ions, but these are initially adsorbed ions. Ions adsorbed on the metal. Then ions go to solution. So that's what we need. So here goes into solution. That's the next step. So I'm saying the first step rate constant is K1, next is K2. So in order to practice, you can practice like making the first step reversible, second step non-reversible, or both are reversible. So all these are examples. Now, you see the first step. It involves electron transfer, right? So we say this is electrochemical reaction. It's electrochemical step because it involves electron transfer. In that case, this means the rate constant A1 is a function of potential because this means it's an electron transfer is happening. So it's also dependent on the potential. When you change the potential, it can involve it can change the rate at which the electron dissolution is happening. So in this step, the rate constant becomes a function of the potential. Now step two, no electron transfer. So we say that this step is a chemical step. And in this step A2 is a constant, or I can say not a function of potential. Q, when a reaction is given, the first step becomes to identify which is electrochemical, which is chemical step. That's very important. Hence, if we make mistake in writing rate constant potential, rate constant functional potential, and we can get it wrong. So here, when I'm applying a positive potential, oxidizing it, when I'm applying a positive potential, the metal has a tendency to give out the electrons and it also forms ions. These ions, in the first step, gets loosely adsorbed in the on the metal surface. Come to the next step. These adsorbed metal ions are consumed in the next step and they form the metal ions which goes into the solution. Right? So why that is important is here we are considering the active metal has many active sites and part of it is occupied by the adsorbed intermediates. Okay. So the total number of active sites are given by gamma. Now, I told metal has so many active sites. Part of it is occupied by the adsorbed intermediate. And there be any adsorbed. So for any adsorbed intermediate, fraction of the site it is adsorbed is given by theta. I I depend upon the what is that intermediate. If there are multiple intermediates, each of them will have different fraction, right? But all of them add up to 1. So here we have M adsorbed intermediate and its fractional coverage. I'll give us theta 1 because only one intermediate is there. So the rest of the vacant site I can write as 1 minus theta 1. Okay. Now the first step is mass balance. How to write the mass balance of water of the intermediate. we have only, so that is the total active site into the fraction which is getting changed over the time. Depends upon first the formation. So we know there's always a rate of formation minus rate of consumed step. So here this step formation happens and this step consumption is happening. So what is the rate? The forward reaction is formed. So it becomes K1 into the metal surface, okay, which is 1 minus theta 1. Or where only one theta is there. So I can write as 1 minus theta minus, in the next step it is consumed. So it becomes K2 into theta. This is the rate of first step and the rate of next step. Now, when you're doing mechanism prediction using impedance, we are assuming few things in this particular reaction mechanism, and that is linear isotherm, which says all sides are equally energetic and species on the surface that is exposed to solution. The only the species which is there on the surface of the metal gets exposed into the solution and they participate in the reaction. So you have multiple, we think there are many adsorbed intermediates. We say that there is no interaction between the neighboring adsorbed sites. No interaction between adjacent sites or species. Now, the next one is all the sites are equal. That means all the sites have equal probability for the intermediate to get adsorbed. Yeah, so these are the what to say, the assumptions based on which we are going to do the modeling. So for any of the coming session also, these are the assumptions. That is, all the sites are equally active and there's no interaction between the absorbed sites and all the sites are energetically equally. And only those species that are there on the surface exposed to solution can participate in the reaction. But there is another isotherm. So this is all based on laminar isotherm. There is another isotherm. This is Temkin isotherm. This is different from the Langmuir system and it accounts for the interaction between the adjacent species. So here, according to which the sites are different energy. Surface having irregularity, and you have species getting absorbed easily on some sites and not on other sites. There is another isotherm which is Fromkin isotherm. So in Langmuir isotherm, we say that only there is one layer of adsorption, but according to which, no, over which another layer can get adsorbed. So here, adsorbed species have tendency to adsorb closer to previously adsorbed species. This means there is interaction between the adjacent species. So these are the different isotherms, but we are assuming Langmuir isotherm and then deriving the expression. Okay, let's go back to where we stopped. So I had to tell those so that we can. So here I'm going to write the mass balance equation once again for continuity. That becomes gamma d theta by t dt equal to k1 1 minus theta minus k2 theta. Now we are going to consider steady state. So at steady state, what happens? D theta by dt equal to 0. And at steady state, we usually, the DC current is applied. So the K1 becomes K1 DC, K2 becomes K2 DC? No, right? Because it's a chemical cell. So K2 remains as it's not dependent upon the potential. So it is K2 becomes K2 itself. So if I write it, K1 DC 1 minus, at steady state, theta becomes theta SS minus K2 theta SS. Let me rearrange it. And I have K1 DC by K1 DC plus K2 equal to theta SS. This is the steady state theta value. When K1 becomes very much less than 0 or it becomes very small, it tends to 0, what happens? This value will, this all becomes 0. So theta tends to 0. This means there is no surface adsorbed intermediate present. So basically the reaction is not happening. Or when K1 is very large, I can say I can neglect K2. So theta tends to 1. So the entire surface is absorbed by the intermediate. So here IF becomes 0 and here IF becomes NF K1 DC 1 minus theta SS. So this is how you can, so questions can arise. So this way you can simplify and get the answer. So when you're passing DC current, what happens? The current cannot pass through the double layer capacitor, right? And so when you're applying AC current, the reaction will move fast or slow. It depends. Now let us find out what is IFDC. How do you find out? We already found out theta SS value. So IFDC equal to F, because it's one electron transfer, K1 DC 1 minus theta SS minus K2 theta SS. You have to substitute K1 DC plus minus I can write K1 dc plus K2 theta SS. So for substitute for theta SS, it becomes K1 dc minus K1 dc plus K2. Theta SS is K1 dc plus K2 theta SS. And so that's possible. So basically what I meant is if theta SS is given, you can calculate like this, you can substitute it back. Uh, just give me a moment. Okay. Just sorry, I just made a mistake again. So we initially wrote at what happens. So we already know theta SS. Now the question is what happens at lower potential and large over potential. Okay. So if I write IFDC at when theta tends to 0, what happens? We can see this become F K1 DC 1 minus K1 DC by K1 DC plus K2. Okay. And if I simplify it, then write K1 DC K2 K1 DC plus K2. So basically, IF it depends only on KF K1 DC and K2 for small and large over potential. So if you plot this, this becomes something of this form. Because yeah, and at large that is at small over potential, and at high over potential K1 DC becomes more than K2. You get IF equal to K2 into F, right? This is how it will be. Now we know how to do linearization and how to. So now the next step is to find out the impedance. How do we do that? Let's write the equation. IF equal to F into K1 plus theta minus K2 theta. This is equation. So we know K1 equal to K1 DC 1 plus B1 EAC. We already saw. Now same way, theta can also be written. So how to do the expression for theta? Theta, it is something, it is dependent upon the potential and becomes theta, dou theta by dou E dc into del E plus dou square theta by dou E square at E dc del E square by 2 factorial, and it goes on. What does this actually mean? So if it was a steady state, theta would have been theta SS at steady state. That happens when it's DC potential. When you have AC also applied it with it, the theta value can become theta plus or minus some value because you are applying an AC current. It's not a constant. It keeps on oscillating, so theta will also have its effect. So to account for that, what we are doing is we are going to linearize it. And this is how it comes. Now, it's of the form e raised to x. Same way here, we have theta at EDC plus rho theta by rho e. Small over potential, how it will vary. Then to the past 2, like that goes on. We can truncate it after the second term. And this one, theta at EDC is theta SS. And this one is theta dash. Change in the potential is ADC minus EAC, right? Or the amplitude. So we can write like this. So this one is substitute for theta, And K1 we already know it is this one. Substitute it there and we get AF equal to F into K1 BC 1 plus B1 EAC 1 minus theta SS minus theta dash EAC. Now we have also one more term minus K2. Same way, because it's not dependent upon the potential, it's just K2 theta. So theta is just plus theta dash EFC. I'm sorry. There's something else I had to explain before writing this, and that is the current. Okay, I made a mistake here also. I just realized it now. This term wouldn't come. And why it wouldn't come? Because the rate of the reaction depends only, I mean, the current of the current in the reaction depends only on those steps where the electron transfer is happening. It excludes all the steps in which this is the thing I was saying when you're writing first identify chemical and electrochemical step and so you'll make a mistake. So I made the same mistake. So here, when you're taking the mass balance, you'll account for the formation and consumption of theta. When it comes to current, what I forgot to correct it over here, although I did it from here. I did it from here explicitly. I forgot to say why I had cut it. I recollected that just now. So here, the second step doesn't have an electron transfer, so it doesn't contribute to current. So this term won't come. Okay, it will just have K1 into 1 minus theta. So now let me simplify it. F into K1 DC 1 minus theta SS. I'm just gonna rearrange it. So E is really small. So easy square is going to be even more small. So we can neglect that term. So here also K1 DC is common in all the terms. With EAC, I'm going to take it out along with EAC into A1 minus B1 theta SS. There's going to be one more term which I understood. Theta dash EAC. Okay. Always when you're doing the derivation, it's better do it on your own and then cross check with the final answer. Because everyone will be doing it in different way. So let me take, so if you see this one part, this is IF DC. So what is IF AC? F into K1 DC AC. Let me write B1 minus B1. So it is B1 into 1 minus theta SS if I write it minus theta dash AC. So this is IFAC. Because this part is IFDC, you know IFAC. Now the next part is what is theta dash. Now how do you find out the theta dash? Theta dash can be found out by finding out how. To find the theta dash, what you have to do is, you know, dou theta by dou t. That is theta dash, which is dou t by dou e to dou e by dou t. Now what is dou e by dou t? To get this, what you can do is T equal to EDC plus EAC naught sine omega t. Now let me differentiate it with respect to time. It becomes 0 with the constant EAC naught and you get omega sine omega t plus pi by 2. So writing cos omega t, I will write like this. I can also write this as EAC is equal to EAC naught sine. Instead of writing EAC naught sine omega t, I can also write an EAC naught e raised to j omega t, right? So dou E by dou t can be written as j omega EAC naught e raised to j omega t, which is j omega EAC. The idea is either you can express like this or you can also express it like this. It depends on the way. Here I wanted something in this form because it's easy for substitution. If I substitute it back in dou theta by dou t, it becomes dou theta by dou is theta dash j omega EAC, right? Now, why this is important? You have the first mass balance equation, this one, right? You can go and substitute this equation for dou theta by dou t. You can substitute this one and find out an equation for theta dash. If I do that, gamma dou theta d theta by dt equal to k1 1 minus theta minus k2 into theta. Gamma, this becomes j omega theta dash EAC equal to k1 dc 1 plus b1 EAC 1 minus theta ss minus theta dash EAC minus k2 is as such. This is theta ss plus theta dash EAC. Open the bracket k1 dc 1 minus theta ss minus k1 dc theta dash EAC plus k1 dc b1 EAC 1 minus theta ss minus k1 dc b1 theta theta 1 k1 dc b1 theta dash EAC square. So this from first one. K2 theta SS minus K2 theta dash EAC. So what you have to do is you have to first cancel out all the constant terms. And this is a constant. Okay. This is a constant. Now all the terms where the second power comes, that can also be neglected because theta AC is already a small value. Now rearrange it. Gamma j omega theta dash EAC becomes equal to minus K1 DC theta dash EAC plus K1 DC B1 EAC 1 minus theta axis minus K2 theta dash EAC. Remove EAC from all the steps because all this having EAC. Now take all the steps which has theta dash to one side. This one has theta dash, this has theta dash. Theta dash is j omega gamma plus K1 dc plus K2, which is equal to K1 dc B1 1 minus theta SS. Now theta dash equal to K1 dc B1 1 minus theta SS j omega gamma plus K1 dc plus K2. This is your expression for theta dash. Now when omega tends to infinity, you have d theta by dE tending to 0, and omega tends to 0, you have d theta by dE tending to real value, right? From this equation. Now this is the theta dash value which should go into this equation. So now if I write this theta dash equation should go to IF F into K1 dc B1 into 1 minus theta SS minus theta dash EFC. This theta dash value is this one, and EAC is there. If I write IEF, so Z value is IAC by IF, which is equal to 1 by F K1 dc B1 1 minus theta SS minus theta dash. So we know the impedance is this one, and when you have both the omega, what to say, CDL and the Faraday reaction, it becomes the sum of the Faraday reaction plus 1 by CDL value, right? Yes, so this is all about the impedance. Now, there is another reaction also that we can look into, and that is a two-step mechanism. This, if we have time, we can see some other time. But let me move on to the assignment questions now, right? So I hope you have understood how to move ahead. First step becomes right mass balance. Then at steady state, find theta SS. Then you have to write IF equation. Find out what is IF AC, right? Then you can write the equation to find out theta dash. Finally, find out the impedance. This, so one thing to keep in mind, find out which is electrochemical, which is chemical step. This is important. IF, the current equation accounts only for the electrochemical step. Steady state value for finding out the mass balance. This accounts for formation and consumption of theta. So both electrochemical and the chemical step is considered. So this is a basic understanding. Now let's move on to the assignment questions. Give me a moment. I have taken the assignment questions. Consider an elementary reaction which says M2 plus 2 electron gives M. So it's a single electron, two electron transfer reaction. It's in a single step. M is a metal, M2 plus solution, the solution going to the solution. Okay. Static current density due to metal deposition. So you have to find out the Faraday current. So here both the steps are electrochemical steps. Right? No problem with that. So what is the rate of the forward reaction? F into rate of the reaction. So the forward rate of the reaction, it becomes K1. So N into F. So here N is equal to 2. So it becomes 2F. So is M2 plus solution. K1 M solution 2 plus minus. What is the backward reaction? K minus 1 into 1. M is a metal, we take it as activity is 1. So unlike the previous year, there is no adsorbed intermediates form, the entire surface of metal is available, so its concentration or the doesn't become like, so we don't have to write it also the adsorbed intermediate. So this is how the expression comes. So NF into forward reaction is K1 into concentration of N2 plus minus backward reaction K minus 1. Yeah, so this is what the equation comes. Now the next step. So here it is K1, K minus 1, M solution 2 plus, and it forms 2 electrons. Now values of K10 is given as 10 to the power minus 9 centimeters square per second. B1 is given as 20 volt inverse. B minus 1 is equal to 18 volt inverse. Concentration of M solution 2 plus given by 25 millimolar. Now determine what is K minus 1. So how to do this? So here the question is you have to find out the rate constant, the K10 for the backward reaction. So what is K10? So here the rate of the forward reaction should be equal to the rate of the backward reaction, right? K1 into the constant rate of forward, okay, let me write as rate of forward reaction equal to rate of backward reaction, which is K1 into concentration of the metal. It's a single step and no adsorbed element, so it is 1 equal to K minus 1 into concentration of M solution 2 plus. Now, you know K, any K equal to Ki e to the power B into E. E to the power B into E becomes constant on either side, gets cut. So I can write this as K10, K minus 10, and M solution 2 plus. Now let me substitute. K10 is 10 to the power minus 9. And yeah, 25 millimolar K minus 10 is to be found. You have 25 millimolar, which is equal to 25 into 10 to the power minus 3 molar. And I think the conversion is given in the question itself, but in part 3 of it, which is 10 to the power minus 3 mole per centimeter cube. So overall it is 25 into 10 to the power minus 6 mole per centimeter cube. Why am I converting? Because here K10 is given in centimeter square per second. You can either convert it to meter square per second and solve, or you can convert the molarity or the concentration to mole per centimeter square and then solve. Now, what is 10 to the power minus 9 by 25 into 10 to the power minus 6? Comes 10 to the power minus 3 by 25. So if I solve this, I'll get it as 4 into 10 to the power minus 5 mole per centimeter square per second. So the question already asks us 10k minus 10 equal to dash into 10 to the power minus 5. So the answer you have to write is just 4 and not into 10 to the power minus 5. This is the answer. Okay. So you can expect such numerical based question also from this portion. So question 3 is magnitude of the anodic current density E equal to 0.3 volt versus equilibrium potential is dash milliampere centimeter square. So I have to find out what is IS. IS equal to NF into rate of the reaction. So I have to first find out what is the rate of the forward reaction. Forward reaction is K10 e to the power B1 EDC K1. K1 value becomes, let me find out all the individual values and then we'll find do the calculation. So that is 10 to the power minus 9 exponential of 20 into 0.3. So 10 to the power minus 9 into 403 is the value you will get. Okay. Exponential to the power 6. Just let me move on. So, yeah. Now K minus 1 is equal to K minus 10 e to the power B minus 1 ADC, which is, so only if you get this first part correct, you will get the next part. 4 into 10 to the power minus 5 exponential of 18 into 0.3. So exponential minus B minus 1 ADC. So So this value, this particular value, I'm getting 0.0045. This into 4. So you should get 0.018 into 10 to the power minus 5. Now, you know the rate expression becomes K1 minus K minus 1 M solution 2 plus. So that is 403 into 10 to the power minus 9 minus, if I write this 18 to 10 to the power minus 8, what is 25 into 10 to the power minus 6. So if I'm doing it individually, each part by part, mm, so this is how we have to solve this. Substitute, and if I'm doing it individually, I've done this. The anodic current part, that is a forward reaction, you will get around 78 milliamp per centimeter square. And the backward, you will get around, what is it, asked value? You will get a very small value, like zero point 0.9 microamp per centimeter square. Now you can see 10 to the power 8 and 10 to the power minus 6 is coming. If you solve it, you're going to get microamp per centimeter square. So value is going to be 78 milliamp, roughly 78 milliamp per centimeter square, because this value is very small. So when you do it, finally your answer should be lying between. Sorry, the question is asked specific to magnitude of cathodic current density. So I've shown you how to do both anodic and cathodic. Wait, because your anodic current density is going to be NF into forward reaction K10 e to the power B1 EDC, and IF cathodic equal to NF K minus 10 e to the power minus B minus 1 EDC into M solution 2 plus. That is N value is gonna be 1, right? Sorry, 2. We get 2 into 96, 485, and K minus 10 to e to the power minus B minus 1 EDC. I've got plus 0.018, 10 to the power minus 5 into M solution 2 plus is 25, 10 to the power minus 6. 50, 96, 485 into 0.018 into 10 to the power minus 11. 50 into 96, 485 into 0.018. Just 8.6, 1, 2, 3, 4. Yeah, 10 to the power minus, I've got 8.6 into 10 to the power 4, this value, into 10 to the power minus 11. When I do that, I am getting 0.86 into 10 to the power minus 6. Because 4 and 11 minus 7, it is minus 7. So I'm just taking one decimal this side, minus 0.86 into 10 to the power minus 6. So that is 0.86 microamp per centimeter square. This is the value I'm getting. I initially thought you had to find the total current density. That's why I did this step. If you had to do that, you have to do something like this. Because only cathodic is asked, you have to only consider the backward reaction. Okay? So I think all this were okay. So next question is question 5. When kinetics is rate limiting, Faraday impedance of simple electron transfer reaction is modeled using. So it is a direct answer. It's a resistor. Okay. Now let's go on with question 6 to 10. They're all linked. Let's do it. M adsorb plus electron. So both the steps involves. No, only the first step is a reversible reaction and that involves an electron transfer. So you have to account for that. Second step is again a electrochemical step. So yeah, so there are many such questions you can do with a CEC kind of once you only you have practice. So let's write the mass balance equation first. Gamma dot theta 1 by dt equal to the first step adsorbed intermediate is formed K1 only one adsorbed intermediate K1 into 1 minus theta minus next step it's consumed K minus 1 theta and the third step again theta is consumed so it's minus K2 theta. So this becomes the answer to your sixth question. First step, forward reaction, M of is formed. Backward, the M theta, M of is consumed, so it is negative. Third step again, M of is consumed, so it's again negative. Now what is the next step? Fractional steady state. So how do you do that? Equate it to 0. So K1 dc, 1 minus theta ss minus K minus 1 dc, theta ss minus K2 dc, theta ss equal to 0. So it becomes K1 dc by K1 dc plus K minus 1 dc plus K2 dc equal to theta ss. Just simple rearrangement. Okay, you got that also. Now the next step is to find out the Faraday impedance. Sorry, IF value. This accounts only for the first step because only that has what to say the electron transfer. That's K1 minus K minus 1 theta. That is option number 2. Now your next step is in the same mechanism you have to find out dou theta by dou E or theta dash. So how to do that? You have to go to the mass balance. Dou theta 1 by dou T is equal to J omega gamma theta dash. So mass balance equation J omega gamma theta dash equal to K1 dc 1 plus B1 EAC 1 minus theta SS minus theta dash EAC minus K minus 1 dc 1 plus B minus 1 EAC theta SS plus theta dash EAC minus K2 dc So that is not dependent on potential because it's a chemical step. It is only K2 theta SS plus theta dash EAC. Now let me rewrite it. K1 DC 1 minus theta SS minus K1 DC theta dash EAC plus K1 DC B1 EAC 1 minus theta SS minus K1 DC B1 EAC square theta dash minus K minus 1 DC theta SS minus K minus 1 DC theta dash EAC minus K minus 1 DC B minus 1 EAC. Next term is cancelled because it has EAC square. I'm not writing it. Minus K2 theta SS minus K2 theta dash EAC. All the constant terms cancel. This is a constant. This is a constant. This is a constant. Now let us cut out EAC from all the sides. J omega gamma theta dash. EAC gone, EAC gone, EAC gone, EAC gone, EAC gone. Now let me rewrite all the terms with theta dash. So this term has theta dash. This term has theta dash. This term has theta dash. Theta dash J omega gamma plus K1 DC plus K minus 1 DC K2 equal to this one K1 DC B1 1 minus theta SS minus K minus 1 DC B minus 1 to theta SS. So is this the answer which is coming? K1 DC B1 1 minus theta SS K minus 1 DC B minus 1 theta SS by J omega gamma plus K1 DC plus K minus 1 DC plus K2. So this is the expression for theta dash or dou theta by dE. Now what is the expression for Z dash? So first you have to write the IF. IF is F K1 1 minus theta minus K minus 1 theta. Now what you can do is F K1 DC 1 plus B1 EAC 1 minus theta SS minus theta dash EAC minus K minus 1 DC 1 plus B minus 1 EAC theta SS plus theta dash EAC. This is the overall expression. Now separated F K1 DC 1 minus theta SS minus, I would prefer to write the minus here, K1 DC theta dash EAC plus K1 DC B1 EAC 1 minus theta SS. The next term gets cancelled because of EAC square. I'm not writing. Minus K minus 1 DC theta SS minus K minus 1 DC B minus 1 EAC theta SS and minus K minus 1 DC theta dash EAC. So if you see K1 DC 1 minus theta SS minus K minus 1 theta SS, that is nothing but it is IF DC. So I'm going to neglect this term and this term. So IFAC becomes F. There is a negative term. Yeah. F into K1 DC B1. So EAC is common. I'm going to take it out. 1 minus theta xs. This is the first term. The next term, if you see, it is K minus 1 DC B minus 1 theta xs. There's all these terms theta xs. I'm going to just write that separately. This term I've written. You see, there are two terms with theta dash. So where theta dash is in common, I'm going to take theta dash outside, and beside that is K1 DC plus K minus 1 DC theta dash or d theta by dE whole into EAC. So what is ZF going to be? ZF is equal to F B1 K1 DC 1 minus theta axis minus B minus 1 K minus 1 DC theta axis minus K1 DC plus K minus 1 DC d theta by dE. So this is the expression for ZF. So if you are doing it fast, you get some experience in how to do this. It becomes easy for you to solve it. Okay. So yeah, this is for today's assignment. I think it is easy. It's just step by step. Like first you will write the material balance equation, and that is gamma equal to, okay. Then find out the steady state. That is the next step. Next one, find out the current. It amounts only for the electrochemical step. So total current you have, you need to obviously find out IFDC, IFAC. That is your kind of fourth step, I would say. That will have theta dash. So for that, you have to find out from the mass balance equation. Finally, impedance. This is a step which is involved and it has to be done systematically. If you are careful, you will not make any mistake in that. Only thing you have to keep in mind, mass balance, it involves the accounting for all the steps in which some species are consumed and formed, the intermediate. But when it is IF, Faraday current, you only account for those steps where electron transfers happen. So yeah, that's all for today. We will meet for the next class. Thank you.